Hi everybody, welcome to the lecture of downstream processing in biotechnology. This lecture we will focus on the membrane filtration. Membrane filtration. The membrane filtration that is used, most used in the unit operation for the downstream processing. That's why we use this to separate, to concentrate, and to purify of the product. That's why mostly we use to separate solid liquid separation technique. We use it to remove cell or cell debris aside, or concentrate the protein, virus. We separate the precipitate after precipitation, as we use purify or clarify the solvent, exchange the buffer and desalting. That's why we remove the salt like this. That's why at the conventional filtration, like membrane filtration, is a pressure-driven fluid flow to separate component in a mixture. That's right. For when you compare with the filter and membrane, that's right. Some membrane is also using the pressure driving, similar to the filtration, but in some membrane is due to the driving force, it's different in concentration. That's right. It's different in concentration, and membrane can use to separate a very small particle small particle size, and also in the very small due to the molecular diameter. That's in the molecular level that the membrane can be used separate solid, also used at different in the molecular level, but filter is only in the micro size, something like this, microscopic size like this. Okay. For the membrane, as I also use the separate, but membrane is also is selective. That's high selective. It's just like membrane separation are generally not high selective. Sorry, okay. At different substance with similar property, it may be co-retain or rise to pass with the desired product. Membrane filtration is particularly suited for like the product concentration application. That's right. But the advantage of membrane, that's right. For example, the membrane is like the low energy. That's right. The membrane we use low energy, and also we can operate like aseptic condition. Aseptic condition that we can operate like to separate the microorganism, to separate the disease or infection, something like this. We can use this membrane for the aseptic condition. That's right. And also membrane can operate either batch or continuous process. Batch or continuous process. It also can easy to scale up. So, but there are some disadvantage of membrane. That is, if we exposure to the harsh chemical, that's right, harsh chemical, that as a strong chemical or strong pressure, higher pressure, lower pressure, or higher temperature, it may be sensitive for the membrane. This is the disadvantage of the membrane. That's right. And also another disadvantage, there are some like the fouling. That's right. The fouling membrane is maybe has limit resistance to cleaning chemical. So when a pH lag, something like this, this also can be damaged by fluctuation of operating pressure. This is some the disadvantage of membrane. That's right. This slide show you right the membrane filtration operation can be classified according to the size of particle or the molecule that's retained by the membrane operating pressure used in the nature of the material filter. For example, right, for this, if we talk about the conventional filter or like filtration, that's like filtration, mostly the particle size that can retain in the filter is mainly greater than 10 micrometer. That's like 10 micrometer until millimeter. This is the conventional filter. Okay, for the membrane, okay, like microfiltration is membrane operation, ultrafiltration, reverse osmosis. We can operate to separate the particle size that is less than 10 micrometer. Like for example, like for microfiltration, we can use to separate start from mammalian cell, yeast, blood cell, bacteria, things like this. And also you can use ultrafiltration or reverse osmosis. It's also membrane in the field of molecular level, right? From 1000 angstrom, for 1 angstrom, reverse osmosis is maybe 10 to 1 angstrom, for example, right? For example, like we can separate like water, sodium chloride, sodium ion, chloride ion, organic acid, glucose, vitamin, for example. This is show you like the classification of membrane based on the size of the particle. And also if we classify based on pressure, that's right. For the conventional filtration, the pressure operates as lower than 0.5 atm. For microfiltration is 0.5 to 2 atm. That's like for ultrafiltration is maybe 2 to 10 atm, and reverse osmosis is 20 to 100 atm. You can see that if the particle size that's retained in the membrane is decreased, you have to apply pressure is greater. That's right. Pressure is increased when the size decrease, something like this. Okay. Okay, I will talk to you for each type of membrane, like microfiltration. Microfiltration that we can use to remove the particle. The size of particle that can retain in the microfiltration is maybe between 0.2 to 10 micrometer. That's it for microfiltration. And ultrafiltration can also be used to separate the solute or particle in the molecular level, right? It's about 0.01 micrometer or 10 angstrom to 100 angstrom. That's between 0.001 micrometer to 0.1 micrometer. This is the ultrafiltration. That's like ultrafiltration. For example, we use ultrafiltration for separate the colloid or large molecule, for example, as protein, polysaccharide, virus, that's like including body from smaller solute and water. This is the application of ultrafiltration. And for microfiltration, we can use to separate like cell homogeneous. Cell homogeneous means the cell after you disrupt the cell. There are some very, very small cell after disruption. You can use the microfiltration to separate. That's a micro to separate. And another is reverse osmosis. Reverse osmosis, or sometimes we call like hyperfiltration. The diameter of the pore should be 1 to 10 angstrom. That's right, 1 to 10 angstrom. The reverse osmosis, for example, like this, the reverse osmosis. Reverse osmosis, we use the pressure to separate. For example, like we have right this solution. For example, sodium chloride solution. This is water. That's right. You apply pressure for reverse osmosis, you can separate water from sodium chloride solution. That like the water can be transferred from this to this. That like this is the reverse osmosis. If we talk about the osmosis pressure, the water from the lower concentration of pure water, that's right, from pure water can transfer to the aqueous solution of sodium chloride, something like this, reverse osmosis. This for osmosis, and this reverse osmosis. From the high concentration to the lower concentration, from the high concentration to the pure water, something like it. You can separate it. Yes, you can separate it. We can separate the salt. That's why we can use it to separate the salt from water, something like this. Okay. Right. Another example of membrane we have is high performance tangential filtration. That's right. High performance tangential we use this is to enhance the ultrafiltration process to activate protein fractionation. We can use this high performance tangential flow to separate protein and protein. If we have a lot of kind of protein or we have a mixture of protein, just like we have lysozyme mixture albumin, we can use this to separate two kind of protein. That like two kind of protein. For this case, we have used the membrane with a charged membrane, which is highly selectivity than normal ultrafiltration. That's like nano ultrafiltration. Also, we can utilize a modified form of reverse osmosis, nanofiltration. That's why we can use nanofiltration to separate ion for a small molecule such as sugar base. That's right. For this case, we mix between the charged membrane and side membrane. Side membrane is mean we separate by the side of the pore. That's right. For the charge, we can separate by the charge of solute that interact with the charge on the membrane, something like this. And also membrane affinity filtration. Membrane affinity filtration is look like the chart, but the membrane is modified by some activated carbon or ligand. That's why we have a ligand or activated carbon attached in the membrane. That's why the solute that we would like to separate is also interact with the ligand. That's why or can be absorbed by the activated carbon. What is get is the membrane affinity, like you show in this for tangential flow. For tangential flow filtration, this is the flow is in the cross flow. That's this is a membrane. That's right. This membrane. This is the tube. That's right. The flow of the feed. We would like to separate its flow in the cross sectional. That's right. The cross flow. The cross flow in this direction. This is for the configuration of tangential flow filtration. That's right. Okay, if the feed is flow across the membrane, that's like across the membrane, the solute or solvent that can pass to the membrane pore, we call this permeate. That's right, can permeate the output that we can retentate. Yes, we can call this retentate. Retentate may be good like the solvent and solute that cannot pass to the membrane. That's right. Okay. And it is the configuration of membrane affinity filtration. You can see that I talked to you is maybe like the surface of the membrane we modify with some ion exchange. That means for if you do the ion exchange, some solute that can exchange between the ion of solution and membrane surface. That's right. And also bioaffinity. Bioaffinity is the ligand attached to membrane. That's right. Some solute that can interact with the ligand. That's right. Or bonding with the ligand. Okay, you can separate that solute. That's right. And also this MPI affinity is the polymer. That's right. Some polymer attached to the surface of membrane. We call this is the affinity filtration. Affinity filtration means the membrane surface attached with some chemical or charge or polymer or ligand that is selectively some solute. That's right. Selectively to the some solute. This is the affinity filtration. Right. Okay. As I talked to you previously, that's like there are another operation of the membrane. There's a dialysis, electrodialysis, osmosis. That's right. Dialysis is also is the membrane filtration. We use like the diving force is maybe different of the solute concentration. That's right. Dialysis we use the different of concentration. Mostly the concentration is higher concentration and lower concentration. The method of solute will transfer from higher to lower concentration. Diffusion dialysis. And also electrodialysis is also a diffusion, but this is due to the electromotive force to drive the solute from higher to lower. And also osmosis. The osmosis we use the osmotic pressure. That's right, to remove, that's right, from the higher concentration to the lower concentration. That's like this the osmosis from the lower concentration to the higher concentration. This is the back pressure. We call it the reverse osmosis. That's right. Like if you back to see this figure, this is osmosis. That's like from the lower concentration, we can apply the pure water or pure solvent to the solution. We did the osmotic, and reverse action is from the higher concentration to the lower concentration or higher to the pure solvent, something like this. This is the osmosis and reverse osmosis operation. Right. And this show you a dialysis. Dialysis, I talked to you that this is based on the diffusion mass transfer. That's right. We have some the cast ion membrane. That's for this is the this case we throw water flow in and spent acid flow in to counter contact. That's why this membrane. For this case, this membrane, that's why this membrane acid ion and hydrogen ion can transfer, can move or can transfer across the membrane from this direction to this direction. That's why from this direction, because we use water in this. That's why we use water. We would like to separate some acid ion. That's right, some acid ion. Okay, some acid ion and some hydrogen ion can diffuse from this, and the resultant is maybe metal ion. That's right. Okay, for this case, we can separate the metal ion from the acid mixture from the solution. That's right. We use the cation membrane, and also we use the water for this. That's right. For this case, some hydrogen ion also diffuse to the water. Acid ion some diffuse to the water, except metal ion cannot diffuse through the membrane. Okay, we can separate metal ion. We can use it to treat the water treatment. That's right, water treatment. Okay, for this kit, electrodialysis. Electrodialysis is use the ion, that's right, or electrical charge. That's right. For this case, we have anode membrane, cathode membrane. It is the positive ion, this negative ion. If you feed solution in this chapter, right? Feed solution, feed solution, feed solution. And also this is a cation membrane. This is anion membrane. For this membrane is the same charge. Yes, the same charge is not pass through the same charge. The different charge can pass through. That's for example, for positive ion, that's right. Positive ion cannot pass through this membrane. That's right. Positive ion can, okay, backward. That's right. For negative ion, okay, can pass through this. Positive, that's right. For this positive come to this, positive come to this, negative, that's right. This is the our exchange that from you go to this, that's right. For this case, there are some high concentration. This high concentration, but for this it is dilute. That's right, dilution. Some solute diffuse this chapter, this chapter, this chapter. Okay, this and some solute come to this, but it's only some the dilution. That's right. The dilution is only the solvent. Okay, we can separate the solute from the solution for that case. It's due to electromotive. That's right, electromotive force or electrical force. That's right. We use the membrane with ion, positive ion, negative ion, something like this. Okay, the generally about the operation, we have two kind of the flow. The first is descent flow and cross flow. Descent flow means that the flow perpendicular to the membrane, this direction, that's right, perpendicular to the membrane. The cross flow is parallel to the membrane, that's right. This is the direction of the flow. Okay, this is generally we have two kind of the flow, is the cross flow and descent flow. It's the same conventional filter. That's a conventional filter. If we use the descent, it's maybe the blocking. That's right. Some blocking to the pore of the membrane. That's right. Pore of the membrane. Okay. This is the cross flow. Both of these there are some the cake accumulate to the surface. If we flow continuously, there are some cake solid accumulate to the surface of the membrane. That's right. It's also if there are some cake accumulate to the membrane. Okay. For this case, there are if we for contract until the membrane, that's right, a lot of kind of solid accumulate to the surface of the membrane. We call this cake. If the thickness of the cake increase until it to be the gel. That means if you feed further, it may be difficult to separate. That means solute or solvent is difficult to flow across the membrane because the pore of the membrane is very small. That's right. Or there is less pore because it's only blocked with the solid, and also we have some gel cover the surface. It's difficult to diffusion. It's difficult to flow. That's right. Across the cake, across the membrane. For this case, you have to regenerate the filter. That's right. You have to regenerate by remove the cake for that case. That's right. Okay. The material that used to produce the membrane, there are lots kind of material. It may be polymer or ceramic. For example, like polysulfate, polyester sulfate, polyamide, that's right, polyacrylic nitride, polyvinyl chloride, something like this. And also we can use biopolymer like cellulose state, or ceramic to be the membrane. That's right. Mostly ideal membrane is the particle also use rejection characteristic. For the membrane we use to separate solid liquid, that means membrane should reject the solid. That's right. The solid particle also used with the particle size is higher than the pore of the membrane. That's right. This is resistant is variation in the temperature. That's right. It's vary with temperature, with pH or pressure. That's right. pH or pressure. Allow high rates of filtration, has high mechanical strength, and is easy and economic to produce for this case. Right. And the kind of membrane, we have two kind of membrane, symptomatic membrane and asymptomatic membrane. I will show you like this. This is the symptomatic membrane and asymptomatic membrane. Symptomatic membrane at least two kinds, dense compact membrane and also isentropic microporous membrane. Symptomatic membrane, mostly the pore size of the membrane is uniform or is the same size. That's right. The size of the pore is the same or the dense. If we talk about the anisotropic membrane or asymmetric membrane, the pore size is different. It's maybe in the layer, the first layer close to the surface of membrane. This is a very small size, and the next layer deep to the deep to the lower surface is maybe bigger size. It's maybe bigger size. That's right. For symmetric membrane, it's easy to blocking the pore and decrease the performance of the membrane. That's right. If the pore is blocking, okay, the membrane can be not separate because solvent and solute cannot pass through the membrane because it's blocked with solid already. For the anisotropic or asymmetric, okay, the problem with the blocking is lower than the symmetric membrane because if the solute, that's a solvent that's smaller in particle size than the pore, it can flow through the membrane. And if it flow through in this direction, it's easy to drain. That's right, because from small to the bigger. That's right. In the first step, it flow to the small side and then it drain out at big side. Okay, this is the difficult or it's hard to blocking this membrane. That's I did the disadvantage and advantage. Okay, if we back to the symmetric membrane that I talked to, it the pore size of the membrane is uniform diameter. That's a uniform diameter. The surface of the symmetric membrane is difficult. That's right. For this case, it is difficult to remove particle trapped within the membrane. That's right. Filtration using symmetric membrane can be progressive less effect as the membrane become irreversible blocking. As I talked to you already. And asymptomatic membrane, that's right, asymptomatic membrane is the solute passing to the membrane are select at upper surface. That's right. Microwide in the lower depth of the membrane provide high permeability and allow rapid filtration. That I talked to you. That's right. That I talked to you for that case. And asymptomatic membrane operate as screen filter by retaining material at the surface. That's right. Not within the membrane itself. But for the symmetric membrane, it may be attain the material in the membrane itself. That's like within the membrane. That's like that in asymptomatic membrane really blocked in the same way as do by symptomatic membrane. That's like for this case, what does it mean? I talked to you already. That's like the symmetric membrane. That's like symmetric membrane is maybe some block of the solid in the pore of the membrane. That's right. But for asymmetric, okay, asymmetric is maybe less than the symmetric due to the blocking is difficult for blocking because at the top layer is small size. That's right. At the top layer is small size. The particle that is smaller than the pore can flow in that. And also when it go to the next layer, it's a bigger size. It's easy to drain out. That's right. It's difficult to block it for the asymmetric membrane. That's right, asymmetric membrane. Okay. Okay. For the other property of the membrane we talk is the rejection. That's right. If we know that, that's right, the membrane we design to reject some particle or some solute, some substance. That means we have to talk about the rejection or rejection coefficient. That's right. The rejection coefficient is equal to the that's right, rejection coefficient equal to Cr minus Cp divided by Cr. Cr is the concentration of solute, that's right, that flow across the membrane or retain in the feed solution. Cp is the concentration of solute that pass through the membrane or permeate, that's right, or permeate, that's right. The concentration is the permeate. This is for example is membrane, that's right. This flow in, this flow out. This is retentate, raffinate, something like this. And the fluid that flow across the membrane, we call this the permeate. That's right. Concentration of solute in the permeate, Cp. Concentration of solute in the retentate or raffinate is Cr. That's right. R equal to Cr minus Cp divided by Cr. That's right. Divided by Cr. If Cp equal to 0, R equal to 1, what does it mean? All of solute cannot pass through the membrane. That's right. Cannot pass through the membrane. It retain all solute. That's right. Retain all solute. If Cp equal to 1, what does it mean? All of solute that can pass through the membrane. Rejection is 0. That's right. Rejection is 0. Okay. For the design of the membrane. That's right. For the design of membrane, this is the molecular weight or the size of the particle of the solute that we would like to remove. We have to cut off side. Mostly in ideal, that's right. In ideal design for this case, at this side, this is the retention coefficient. Retention coefficient it should be 1. That's right. If the size is greater than this side, that's right. The size is greater than this side. For ideal retention, it go to 1 rapidly. For this case, this ideal. That's right. This ideal. The size that is less than cut off, okay. Less than cut off, the R equal to 0 because all of this can pass through the membrane. That's right, pass through the membrane. But the particle size or molecular weight is greater than the cut off. Okay, this is R equal to 1. All of this cannot pass through the membrane. That's right. But for the reality, that's right, we cannot produce the membrane with its uniform size. We cannot do that. That's right. We cannot use the real uniform size. Okay, it's maybe some like the relative sharp, something like this. Maybe the side around it can pass through the membrane is some parts of the side. That's right. It's also is the cut off. This is relative to diffuse cut off characteristic. This is the sharp cut off characteristic. That's right. But for the real system, the manufacturer that's right, for absolute rating. Rating means the less of the particle size or molecular weight cut off. But for the nominal rating, it's maybe 90% of the ideal. That's right. We can use this about 90% for the cut off. That's right. Allow this. That's right. For something like this, it's maybe we only calculate it's 90% cut off the weight side. That's right. Okay. And also, if you buy some membrane from the manufacturer, that's right, the membrane rating is maybe from the manufacturer aside. From previously I talk absolute rating mean all of the membrane. That particle size greater than the cutoff, okay, is retained on the pore or retained on the surface membrane. But nominal rating that is used mainly ultrafiltration membrane aside. Is expressed is molecular weight cutoff aside. For this case, the normal rating it should be about, I talked to is 90%. That's right, it's 90% for the absolute rating. 90% for absolute rating. Okay. The other factors such as chaff, deformability, charge, hydrophobicity, concentration of solute, pH, ionic strength, and composition of solvent also affect the membrane separation. That's right, membrane separation. For example, like linear or flexible molecules tend to pass through the membrane to the greater extent than molecules of some molecular weight but have more complex globular or branch structure. What does it mean? If the molecule is flexible or linear molecule, it's easy to pass through the floor of the membrane or the whole of the membrane. If the molecule is complex globular, that's right, or branch molecule, something like this is molecule of protein like this, compared to like it. This is difficult to fall through a membrane, but it's easy to fall through a membrane. That's right. For linear, that's right. If you compare or complex molecule, this is also affect the membrane separation. Okay. Mostly the property of the retention property of the particle solute and membrane are determined by experimental. A lack of the pore and membrane characteristics such as the pore size distribution, aside pore density. Pore density is mean the number of pore per unit area of the membrane. Like surface porosity. Surface porosity is the fraction of membrane surface occupied by pore. That's right. Membrane porosity is the fraction of the membrane volume occupied by pore. It's also used to determine filtration rate. That's right. The filtration rate that we determine is the permease flux or rate of solution that's passed through the membrane. We use this at the filtration rate. At the filtration rate. Typically, like the ultrafiltration membrane have pore density is around 10 power 7 to 10 power 10 per square centimeter. That's right. And the surface porosity of microfiltration membrane is usually in the length 25 to 40%. That's right, 25 to 40%. But in contrast, ultrafiltration membrane have considerably lower surface porosity, less than 10%. That's right. In conclusion, the larger and more numerous pore per unit area of the membrane, the greater is the rate of permeate flow. That's right. Large pore or more numerous pore per unit area, okay, it indicate the higher filtration rate, for this. Okay, I will stop this lecture. I will continue for the membrane theory for the next lecture. Thank you for your attention.